Thank you. After that introduction, I feel a little self-conscious that I'm not wearing a tie. Oh well. So I am here on behalf of the assembled list of authors to report on our chapter on the life and times of giant molecular clouds. Now, of course, at the time we wrote this review, JWST was still on the ground, and so we did not have fantastic images like this one from JWST. I have therefore just sort of used them as a backdrop in the talk. So here's the outline of what I'm going to do. I'm going to start with just an overview of what's new since Protostars and Planet 6 in Heidelberg. What has changed? I will then talk about a broad picture of what the observations are telling us about the bulk properties and demographics of giant molecular clouds. And then I will go through the GMC life cycle and end, of course, with future prospects, what we don't understand yet. All right, so let's start with what's new. And of course, with what's new, I'm going to start with the observations. And I can think of few things that would better illustrate what's new than comparing these two images. This is from 2008, and this is the sort of thing we talked about at the last Protostars and Planets meeting. And I mean, that's a pretty good image. That's, you know, right? We've got a map of an entire galaxy in CO. But let's put that compared to the ALMA image of the exact same galaxy 10 years later. All right, so this and this are the same galaxy in the same line, just 10 years apart. Now, you can see, I mean, they're you know, if I zoom into this little patch, that looks like about the same resolution as that. But you can see what a difference 10 years, and in particular ALMA, makes. All right, so what has changed since the last Protostars and Planets meeting? Well, one thing is we got ALMA, of course. At the time of the last Protostars and Planets meeting, ALMA had just come online. We saw like its first images at that meeting. Herschel had just wrapped up observations. It was still being analyzed. We didn't have the full import of it yet. Muse had not yet had first light. And all of these facilities have given us much greater both resolution and throughput. So we now have much more complete maps and with much more resolution than we had before. So we've gone from kiloparsec to 100 parsec resolution in looking at external galaxies. We've gotten resolution-matched maps of molecular cloud tracers with things like star formation tracers. And within the galaxy, we've gotten matched gas and star formation tracers at less than 1 parsec scale. All right, so a theme that we're going to see again and again and again is complete statistics at high resolution, which enable you to do things you just couldn't do 10 years ago. Now, on the theory side, as of the last meeting in 2012 or 2013, this is what a typical GMC simulation looked like. All right, this is actually a very good simulation. I like it a lot. But there are limits. This didn't follow the galactic context, didn't follow chemistry, only included 1 or 2 feedback mechanisms and had fairly limited dynamic range. Since then, the simulations have improved as much as the observations. All right, we now have simulations of GMCs that either include the full galactic context, so you're not just simulating an isolated cloud, but you're simulating a GMC in a galaxy with the full galaxy around it, or that have the dynamic range to go down from a GMC to forming individual stars. Not both yet. We're not quite there yet, but we're getting there. A lot of these simulations include the chemistry, which we're going to see is crucial if you want to get the observables right and do the simulation observation comparison right. And they include pretty much all important feedback mechanisms that control GMC evolution. All right, so here's the big picture. Multi-wavelength measurements of large statistical samples have really transformed this field. And simulations now include enough physics that they can reasonably reproduce a large number of these observations. And so we're getting to the point where there's reasonable simulation observation consensus. Not perfect, there are still points of difference that I'll come to, but things are a lot closer than they were 10 years ago. Most of the open questions, I would say now, really have to do with the fact that we have these data, which are great, but only for a limited range of galaxies, only for things that look relatively like the Milky Way. We know much less about how things work in dwarfs or in starbursts or in any non-Milky Way solar neighborhood-like environment. All right, so let's start with the observations. This is the point where I give you a moment to read my meme here. Take a moment, you can laugh, it's okay. I'm a theorist, I admit it. This is my relationship with telescopes illustrated right here. All right, so a basic question we have to start with, which I think a lot of talks about GMCs have to deal with, is this question of, well, what do we mean by GMC? And part of the problem in this field has been that what we mean by GMC is often a sort of vague blob at our resolution limit. All right, GMCs are like clouds in the sky. They don't have sharp boundaries. They don't have clear edges. All right, there's a chemical edge defined by something like the C to CO or H to H2 transition, but it's unclear that that's dynamically important. Where that chemical change occurs, it's not clear that something physically important is happening there. You can, of course, draw contours like this in dust continuum, but then you have the question of, well, which contour should you choose and why? That's fairly arbitrary, and you can't really do that for extragalactic work anyway. There's, in general, no unique way in a position-position velocity cloud or a cube to define what you mean by GMC. So the caveat is that everything I'm going to say here about the statistics of GMCs is GMCs selected in some way, and there is no really in-principle reason why one way of selecting is better than another. You simply can't talk about GMC properties independent of where you drew your contours or how you selected them. All right, so an alternative approach, which a lot of research has taken, is to simply say, all right, forget defining clouds at all. I'm simply going to give the statistics of, say, pixels. I'm going to pixelize a map of a nearby galaxy and talk about the relationship between the pixels describing molecular gas and the pixels describing star formation or something like that. Or to do contour statistics, to just draw contours and say, here's the relationship within this contour, and you can choose any contour you want. So just keep that in mind for what follows. So what's the current observational state of play? Well, within the galaxy, we've had a bunch of galactic plane surveys. I list a bunch of them here, and those have given us pretty much complete maps of at least large parts of the galactic plane, identifying every molecular cloud. Now, again, the definition of molecular clouds varies from one of these surveys to another because there's no unique way in which to pick out molecular clouds. But you have a sample that is selected using some algorithm which is complete across the galaxy. Extragalactically, we now have tens of galaxies at sort of 100 parsec resolution. Now, these are, of course, necessarily much lower resolution and sensitivity than what you can do within the galaxy, but the great advantage is there's no distance ambiguity, and so you can unambiguously match the molecular cloud maps against maps of other things like H alpha or IR or whatever star formation rate tracer you want. And so you can do comparisons between molecular gas and other stuff with no uncertainties about distance or foreground background. And finally, you have extragalactic surveys in dense gas tracers like HCN, HCO+, N2H+. And these trace gas that's much denser than what your extragalactic CO surveys trace, so they're complementary. The price of this is, again, you're going down in resolution and sensitivity for that gain in information. All right, so what do we learn? Well, first of all, no matter how you define clouds, whatever your cloud definition is, they seem to obey a line-width-size relation. That is, bigger clouds have larger velocity dispersions with a power law relation of about a half, which is what you expect from supersonic turbulence. If you characterize the strength of self-gravity in molecular clouds via the virial parameter, that's this, you find that for low-mass clouds, it tends to be big, indicating they're not self-gravitating. And for massive clouds, it turns over and sort of flattens and becomes of order unity. So what that tells you is that these things are mostly not self-gravitating, these things mostly are. And you might think, well, by number, most molecular clouds are not self-gravitating, and by number, you'd be right. But the mass function is relatively flat. dn dm is m to the minus 2, which means there's actually a lot of mass in these big clouds, even though they're rare by number. So we have a lot of low-mass molecular fluff that's not self-gravitating. We have a small number of self-gravitating massive clouds, but those actually constitute a significant fraction of all the molecular gas in the galaxy. Now, virial parameter here is a crude estimator of self-gravity. It ignores magnetic fields and surface effects and all of this other stuff. Nonetheless, this trend is generally indicative that massive clouds are self-gravitating or at least contain self-gravitating parts within them, whereas low-mass clouds do not. On the other hand, we've also learned that not all molecular clouds are the same. This was a lot less clear at the time of the last Protostars and Planets meeting. It's now crystal clear. While all molecular clouds are roughly self-gravitating, and they all obey line-width-size relations, the normalizations are very, very different from one galaxy to another. And that's illustrated in this figure here, just showing all of these clouds sit along this alpha Vir of 1 to 2 relation, but they sit in different places along it, depending on which galaxy you're talking about. Higher surface density, more turbulent clouds tend to be found in galactic centers or in general in galaxies with more gas. Larger velocity dispersions at fixed scale are found in denser environments. And you can do similar comparisons for arm versus inter-arm clouds, interacting versus isolated galaxies, and all of these things matter. And these environmental effects don't just apply to the CO, they even apply to things like the HCN, and that's illustrated here, where we've got the HCN to CO ratio and the IR to HCN ratio versus molecular gas surface density from the Empire survey, and you see that there's a clear trend. So even if you focus in on dense gas tracers, they're not the same from one galaxy to another. They know about the larger galactic environment. So the big picture of what the observations are telling us is that GMCs are inextricably linked to their galactic environments. We should think of them not as stars that sort of don't care what galaxy they live in, but as the self-gravitating and massive and dense end of the galactic gas distribution. To put it another way, you should think of molecular clouds as like the white caps on waves. All right, so here's the rest of the galaxy. Here are the GMCs. They're the white caps on the waves of the galaxy, which of course leaves us as astronomers here. I've got my, Japan-themed visual jokes throughout because this is the best I could do. All right, so let's talk about, now that we've reviewed the sort of bulk demographics, the GMC life cycle. What do we know about how molecular clouds are born, mature, form stars, and finally die? So here are the top-level questions I want to address. How and why do GMCs form? Once formed, how long do they live, and how long do they spend in various evolutionary phases? How rapidly or efficiently is star formation occurring once molecular clouds have formed? Are they in a state of sort of global, perhaps hierarchical collapse, or are only small subparts of them collapsing? And finally, what eventually ends GMC's lives? All right, so let's start with formation. We have here a simulation of GMC formation by Kim et al. In a spiral arm. And when we gave this talk at the last Protostars and Planets meeting, there was a lot of discussion about different formation mechanisms. And we had this whole laundry list, Tumorian genes instability, converging flows, supernova-driven shell collisions, cloud-cloud collisions, spiral arms, merger compression, et cetera. And what's become clear in the last decade is that, well, really all of these operate, and you can't pick out a single one that's dominant. It's going to vary with environment. But more fundamentally, the reason you can't pick out a single one that's dominant is because galaxies at large scales live in a state of dynamical equilibrium where self-gravity is balanced by turbulence driven by supernova feedback, driven by various other mechanisms. And the fact that turbulence and self-gravity are roughly in balance means no one of these mechanisms could possibly dominate. It means that all of them are going to be about equally important. So because galaxies live in this dynamical equilibrium, all of these things occur, and you can't really distinguish and say, oh, that cloud formed by tumor instability and that cloud formed by supernova shell collision. It's not clean where one mechanism or another dominates. All right, so part of forming a molecular cloud is dynamics. You have to bring the mass together, but another part is chemistry. After all, if you're going to form a molecular cloud, you need to form molecules. Well, so what's involved in that? Well, you need to transition from H1 to H2, and to do that, you need to block out the background interstellar radiation field. In fact, in order to get to an H2 dominant composition, you need to reduce the dissociation rate from interstellar radiation by about 4 decs. Now, what can do this is partly self-shielding, but it's partly also dust. And because dust is important, the transition from H1 to H2 is metallicity dependent. Metal-poor galaxies require larger columns, and you can see that very clearly in this observation. So it's plotted here from Schrube et al. Is total gas surface density versus H1 surface density, and you see this pattern that you fall along the one-to-one line more or less at low surface density, but then you flatten and reach a maximum H1 surface density. And what's happening there is everything up to this turning point is H1, anything you add beyond that is H2, but you can see where this turn occurs depends on metallicity. It's higher at lower metallicity. And this is simply because you need to reach a higher column of dust to reduce the dissociation rate enough to undergo the chemical transition. So you can see that very clearly in these data. Now, the timescales for chemical changes at dynamics are similar. And so ideally, you do both chemistry and dynamics together, as done in this simulation I'm showing from Steffi Walch et al. All right, so this is a chemodynamic simulation, and this is sort of the state of the art in GMC formation, in that you do the chemistry and the dynamics at the same time, and you can see here the various chemical species. Now, turns out, under solar neighborhood conditions, equilibrium is not a terrible assumption. Things aren't too far from equilibrium, but ideally you do the chemistry and the dynamics together. And in fact, the current state of the art is to do the chemistry and the dynamics together using a reduced something like HCO chemodynamic network, and then also at the same time or afterwards do post-processing to capture non-LTE effects when you're calculating the observable line emission, because it turns out that non-LTE excitation is quite important, particularly for the isotopologues of CO. So that's the state of the art when it comes to GMC formation. What about evolution? So a huge breakthrough that has occurred since the last Protostars and Planets meeting, coming out of having these large homogeneous samples, is that we have now available to us new statistical techniques to characterize the timescales of GMC evolution. All right, so in the past, people had tried to do this by using stellar age spreads or by using orbital markers, for example, looking at where GMCs were relative to bars or spiral arm shocks. But the real workhorse has been this correlation between star formation tracers and molecular gas tracers. And it's illustrated here in this plot from Krausen et al. Called the uncertainty principle, and the basic idea is the following. You look at big apertures, and there's some average ratio of CO to star formation tracers. And that's telling you about the average depletion time, how long it takes to turn gas into stars averaged over a galactic scale. And you get some galactic average. But if you zoom in on either maxima of gas or maxima of stars, this average starts to come apart. You get what's called this tuning fork diagram. And the shape of the tuning fork is sensitive to the relative duration of molecular clouds compared to the duration for which, say, your star formation tracer comes on. So for example, if you're using H alpha as your star formation tracer, well, that traces stars that stay on for of order 4 million years, and the relative number of H alpha versus CO peaks is telling you something about how long molecular clouds live compared to how long H alpha stays on. And so you can use the statistics to derive the lifetimes of GMCs. And when you do, you get something like this. And so the basic picture you should take away is that molecular clouds are moderately short-lived. There used to be these huge debates about do molecular clouds live long times or short times? The answer is somewhere in between. The typical lifetime is 20 to 30 million years, which in terms of freefall times is like 1 to 5 freefall times. Dispersal is fast. Once H alpha actually becomes optically revealed, or 24 micron, the molecular cloud is usually gone in less than a freefall time, less than about 5 million years. But there's a long time where, at least at extragalactic distances, you are not seeing large amounts of high mass star formation indicative of lots of feedback. And that's actually a lot of the molecular cloud's life. So I'd say we now have a pretty good idea of how long molecular clouds live, at least on average. These are averages for, I should emphasize, the mean molecular cloud. They can be different depending on what mass you're talking about. I'd say we also have very clear ideas of how quickly mass turns into stars in molecular clouds. So the fundamental thing you want to measure here is this quantity epsilon FF. It's what fraction of the mass is transformed into stars per freefall time. And that per freefall time is critical because molecular clouds aren't well-defined entities. If you choose to focus on, for example, 13CO or C18O, you're looking at much denser gas than if you're looking at 12CO. If you look at high-density dust extinction contours, you're not looking at the same gas as if you look at an extragalactic 12CO survey. So you need to normalize to the free fall time of the gas you're looking at so that you can make an apples-to-apples comparison. And that's why this epsilon FF quantity is important. And when you do that normalization, what you find is that this is always about 1%. And you find this on a huge range of scales. So here is from Hu et al. a plot of epsilon FF versus gas surface density derived for Gould's belt clouds in the solar neighborhood where the gas is measured by dust extinction contours or dust emission, and where the star formation tracer is counting individual protostars. These are measurements from Sun et al., where the tracers are FUV or H alpha, and the gas is measured on galactic scales. And what you see is that this epsilon FF on both of these is about 1%. So you have this remarkably robust result that basically no matter where you look and no matter what tracer or technique you use, this number is always, always, always about 1%. Now there are very interesting variations around that. You see it's not completely uniform. There's a spread here, there's a spread here. And you could ask, well, how real is that spread? How much of it is observational? And it looks like, from the best techniques, the spread is about 0.2 to 0.3 dex. There's potentially some dependence on environment, determining whether you're at the high or low end of that 0.2 to 0.3 dex. But it's a small spread. And there's sort of weak variation, weak evidence for variation with environment. All right, so that's the sort of quantitative thing. The somewhat less quantitative but still important thing you can do, and we'll hear way more about this later, so I'm just going to go over it very quickly, is the sort of morphology and kinematics. When you look into molecular clouds, you often see these dense filaments converging on these star-forming hubs that live, say, there or there, bringing mass into them. And the kinematics indicates that mass is flowing along these filaments to feed the hubs. And you might think, well, is this where most star formation takes place? And the answer seems to be surprisingly no. All right, and the reason is that if they were, then kinematics from Gaia would basically show all stars have radial velocities pointing away from those hubs. And that's not, in fact, what you see. All right, so this plot from Ward et al. Is showing just one tracer, the median value of the radial to tangential velocity vector for stars. Now, if everything was formed in these very small regions and then dispersed away from there, as things disperse, the velocity vectors should become increasingly radial, simply because if you start with stuff that's all confined to a small volume and then let it expand, well, as it travels ballistically over time, its velocity vector points increasingly in the radial direction. And that's what you see for example, this orange line. That's what you'd expect for a large-scale expansion. It looks much more like small-scale expansion. So the takeaway from this paper and from this picture is that there's hierarchical structure, but it's dominated by local, not global collapse. That is, you have these little filaments and hubs where stuff is forming, and you have stars forming in these filaments, but the hubs are not where most of the stars are forming, and most of the GMC is not falling toward the hubs. So that's the picture that comes out of the kinematics. All right, so that's how GMCs form stars. Let's talk about how they die. What kills them? Well, you can think of a few things. First of all, it's just galactic environmental processes, for example, shear or tides. And these are potentially important in regions like the central molecular zone where the shear is very high, but they're not important in most places. They may be important for limiting the rate at which molecular material becomes self-gravitating and goes on to form stars. But these processes alone can't kill molecular clouds in a typical environment. Instead, what has to kill them is stellar feedback. All right, and that stellar feedback, if it's a giant molecular cloud and not a wimpy thing like Taurus, has to be from massive stars. And we have the following mechanisms: photoionization, direct and dust reprocessed radiation pressure, stellar winds, supernovae. All right, now I want to emphasize what I'm about to say here really focuses on solar neighborhood-like environments and Milky Way-like galaxies. The story is potentially different in other galaxy types, and we'll get to that at the end. So, photoionization. Photoionization, the basic mechanism is that massive stars heat gas to 10 to the 4 Kelvin. That makes the gas pressurized enough that its thermal pressure is enough to blow it away from molecular clouds. And the momentum delivered to the cloud by this rocket effect is of order 200 kilometers per second per megayear. It's a lot. And there's significant mass loss as a result. So, for every solar mass I put into stars, on average, I expect to photoevaporate about 10 solar masses of material from molecular clouds. And if I add in the non-ionized material, but that is nonetheless rocketed away from clouds, I get another 30% on top of that. And that's what's illustrated in this simulation of photoionization feedback here by Kim et al. And this is probably the dominant mechanism destroying GMCs in Milky Way-like environments. direct industry processed radiation pressure. Well, all right, first I should explain what I mean by these. So there are two types of radiation pressure you could worry about. The first is just what comes off the stars directly. The radiation field emitted by stars carries a momentum flux of L over C, and it's deposited where the radiation is absorbed. But if the photons are then trapped and reabsorbed many times in the form of an infrared radiation field, then you can get many times that. So you can try and observationally estimate how strong these pressures are, and that's what's done in this work by Olivier et al. All right, and here we have ultra-compact H2 regions, here we have larger H2 regions. The different colors are showing the different types of pressure. And you see at large sizes, the gas pressure dominates. At small sizes, she concludes the infrared radiation pressure dominates, but that's actually a bit of a mystery because the simulations suggest that that really shouldn't be possible, and it's possible that the infrared radiation pressures have been misestimated. Stellar winds and supernovae. Now, these carry very little momentum, but a ton of energy. And so their importance depends on how much that energy gets bottled up. And the energy can be lost via either turbulent mixing or mechanical escape. And simulations seem to show that these mechanisms prevent stellar winds or supernovae from being dominant in destroying molecular clouds. All right, and that's illustrated here in the simulation from Lucas et al. So these are two panels immediately before and immediately after a supernova goes off. You can see the supernova went off because you can see that little blast wave there in the low density gas. But in the dense gas, you see almost nothing, and that's because none of the energy gets deposited in the dense gas. It goes around the dense gas and not into it. So it's very important at galactic scales, but it's not dominant for destroying GMCs. All right, so we're reaching the end, the lifetime accomplishment of a GMC. All right, so we've seen that GMCs are moderately short-lived, lifetime of a few freefall times, but they disperse rapidly once massive stars become visible. They form stars very inefficiently. SFR per freefall time is 1% everywhere it's been measured. And those two things together imply that you only convert about 5% of the mass of a molecular cloud to stars before it's dispersed. There are these regions of filamentary collapse, but most stars do not form in them. Only about 10% remain in bound clusters long term. Contrary to older lore, most stars do not form in clusters. If you take nothing else away from this meeting, stop saying most stars form in clusters. They don't. All right, so what do we get from theory and simulations? Well, the fraction of a cloud that you have to convert to stars before the feedback from that is sufficient to disperse the rest depends on the momentum injected per unit stellar mass by that feedback, and it gives rise to this relation shown by these dashed and solid lines. And simulations sort of roughly confirm that prediction. Higher surface densities require higher star formation efficiencies to disperse. Now, if you put in 100 solar mass per square parsec, typical of the Milky Way GMC, what you get is an efficiency of about 5%, which is consistent with what you need. But there are some problems with these simulations of isolated clouds. The lifetimes are too short. Here are some simulations, for example, from Grudich et al. That get the right star formation efficiency, but none of their clouds live more than about 5 million years, which is too short. And the efficiencies are too high if you put in high surface densities. Now, fortunately, most of these problems seem to be fixed if you include the full galactic context. All right, so here's a simulation from Jefferson et al. Showing the formation of a molecular cloud in a galaxy scale simulation. I'm just zooming in on a small part of it. And you see that there's this continuing inflow of mass. And that continuing inflow of mass seems to be critical to getting the lifetimes right. The fundamental effect is that molecular clouds are constantly losing mass. Feedback is very efficient. But in massive clouds, this is countered by ongoing accretion that resupplies the cloud. And this explains why clouds don't live 5 million years, they live 30 million years, because they're getting continually resupplied for that time. Now, a caveat is that in these galaxy scale simulations, the feedback physics is necessarily treated more approximately than in the simulations of isolated clouds just because of resolution. Finally, once clouds are dispersed, the spatial correlation of GMCs and young stars should be encoded in where the star clusters are. And you see something like that. So here is the 2-point correlation function of GMCs, which are solid, and of star clusters, which are dashed, binned by mass. And what you see is that for the massive clouds and star clusters, they are autocorrelated on scales of 100 parsecs. All right, so the two-point correlation function of GMCs is flat at low masses, but for massive ones, which remember dominate the star formation, it becomes power law-like, and you see that in the young clusters. So this suggests a scenario where stars and clusters are initially quite concentrated, but over time, as they age, their distribution flattens out. And you see this in this plot showing the two-point correlation function of star clusters of different ages, where they start highly correlated at young ages and then smooth out. All right, so we have gotten to almost the end, which is good because I have 5 minutes left. Future prospects and problems. What haven't we solved? What problems will be left for people after I have retired? All right, so first of all, there's the question of what goes on, and I've emphasized this again and again, beyond Milky Way-like galaxies. Almost all of our observations so far are for spiral galaxies pretty similar to the Milky Way, or at most metal-rich, relatively metal-rich dwarfs like the LMC. The SMC is probably the one case where we have good data on really low metallicity stuff, and even that's not that low metallicity. So what does theory suggest? Well, here are some simulations from Rathjen et al. Showing simulations of 100 solar mass per square parsec environment 10 times denser than in the solar neighborhood. All right, and it suggests that the composition should change radically, right? You should be getting a lot more neutral gas, a lot less ionized gas. Conversely, if you go to low metallicity, it should be much harder to form molecular clouds. And there are limited observations so far, but there's some intriguing hints of weird things going on. Like, for example, if you find in H1-dominated galaxies, very low metallicity dwarfs, the depletion time can be ridiculously long, like 5-10 times the Hubble time. So you've got huge blobs of H1 sitting there with no star formation. You might expect that at higher surface density, this epsilon FF parameter would go up. Intriguingly, there's no actual evidence that it does. Starbursts seem to have the same epsilon FF as lower density galaxies. So what's going on? We're not quite sure. Another future prospect, which has already started happening, is that you can use the spatial statistics, now that we have them, of molecular gas and star formation, to constrain how star formation is treated in galactic simulations. So here's a tuning fork diagram, aperture size versus ratio of depletion time in gas and stars. All right, and what's different about this one is that we've plotted observations with the points and then a series of simulations with the dashed lines. And you can immediately read off that some of these simulations do better than others in reproducing this correlation. And what this means is that you can actually test, did I implement my subgrid physics right in a galaxy scale simulation? Or at least you can tell if you did it wrong if you fail to reproduce this. So this is a very powerful tool for checking if your simulations are doing molecular cloud physics right. And finally, we have the observational frontier. What's coming next? Well, in ground-based optical near IR and near UV, we have local volume mapper and VLT Mavis coming, and Blue Muse coming soon, Harmony a little further down the track. And the science that these will enable is line diagnostics that will let us constrain the physics of stellar feedback at high resolution and, crucially, in non-Milky Way-like galaxies. For radio, we have CCAT prime tracing out C1, NGVLA, SKA, and LOFAR tracing out H1. And the science that these will let us do is focus in on the galactic environment and its interaction with GMCs. In particular, we have all this theory and all of this statistical evidence telling us that accretion and exchange of mass and energy with the environment is crucial to GMC evolution. But we can't map that out very well right now because it's all taking place in this dark gas where there isn't a lot of CO. C1 is an ideal tracer. So is optically thick cold H1. These are things we will be able to do. And finally, from space, of course, we have JWST and potentially Athena and Lynx in the X-ray. And these will allow us to study the earliest stages of dust-enshrouded star formation, and for the X-ray missions, characterize hot wind and supernova feedback to see if this picture, that it does nothing because the energy all leaks out, is in fact correct. And I have reached the end. Thank you very much.
now this talk is open for questions. So there is 5 microphones, 1, 2, 3, 5, okay? Could you queue up in front of the microphone to ask a question, please? Okay, well, let's start here.
Mark, very nice talk, but you said something very quickly in passing, which was about if you take nothing else away, stars don't form in clusters. And I'd like to hear a little bit more about that. Could you just sort of riff just a little bit more deeply?
Yeah, so I think we went into this more in the review. I mean, part of the difficulty is that the word cluster is one of these words like cloud or clump, where 5 people use it with 8 different definitions. So stars are certainly born clustered in the sense that if I look at 2 stars that are 1 million years old, on average, their nearest neighbor is a hell of a lot closer than if I look at 2 stars that are a giga-year-old. So they are clustered in that sense, but they're not in clusters in the sense that if your idea of a cluster is the Orion Nebula cluster, the central parsec or 2 of Orion, that's not the environment where most stars form. Most stars don't form at that sort of density in something that is likely to virialize and survive gas removal. You should think of the typical star-forming environment as not the Orion Nebula cluster, but the outskirts of Orion where the densities are a lot lower. And most of that stuff, as soon as the gas is dispersed, probably just disappears.
Okay, move on, yes.
Okay, thank you very much for your talk. And I have a question in line with the previous question. So you also mentioned that observationally we see that the spatial correlation between the clouds and clusters, then maybe in age of as a function of age of the clusters, we may see more separation. Then in that case, like how that will be connected with that idea of star formation in clouds. Yeah.
Right, so this is looking at the fraction of stars that survive in clusters, all right? So as soon as I say we're looking at clusters, 90% of the stars aren't there. This is using the 10% that stay in clusters and tracing their spatial distribution. And the reason for doing this is simply that star clusters are visible at extragalactic distances in the way that individual YSOs aren't. So really you should think of this as using the clusters as tracer particles for the dispersal of stars in places where you can't see individual stars.
Okay, thank you very much.
Okay, let's take the one from the back.
Thank you. I have a question. So if I took the note correctly, you said that the origin of turbulence in GMCs doesn't matter because the different origins, so like supernova feedback, etc., contribute about the same. How do we know that?
So I don't want to say that the origin of turbulence in GMCs is dominated by one or another of these mechanisms. I actually didn't talk about that at all. What I would say is, if you just ask where did the GMCs themselves come from, people spent a lot of time trying to say, oh, it's tomb ray instability or it's cloud-cloud collisions or whatever. And the answer is it's all of the above, and you can't cleanly separate these mechanisms. So I was talking about simply how did you assemble the clouds? I was not talking about the origin of turbulence in the GMCs.
Thank you.
Thank you. Okay, yes.
Yeah, this may also be a question of nomenclature, but one thing I have yet to understand over all these decades is the 10 to 30 or 50 million year lifetime of clouds. And so that suggests one of 2 things. There should be clouds sitting out there in which we see no young stars, or it should suggest that we see stars that we know are 5, 10, 20 million years old with molecular gas. And neither of these things are true in the galaxy. So can you help me understand this classic confusion?
Sure, okay, and I think maybe watching this movie might help. So I'd add a few things. One is that when we say star-free molecular clouds, when we talk about sort of 20 or 30 million year lifetimes, a lot of that lifetime there are no massive stars, or at least no massive stars that are optically revealed so you can easily see them in something like H-alpha. There could well be low-mass stars there. So it's not that there are these molecular clouds that are sitting there inert for a long time with no star formation. It's that there's no star formation you can see in an extragalactic survey. That's not the same thing. Now, as for why don't you see stars with molecular gas, with molecular gas around them for long times? Well, okay, if I play this, or if you look at the simulation movie, you will see that around individual star particles, they blow holes in the molecular clouds. So once you've got something like the Orion Nebula, it will blow a hole in the cloud. And so you won't see molecular gas immediately around it. But a key point here is that the destruction of the gas around the Orion Nebula didn't destroy the entire Orion molecular cloud. So if you look at the Orion molecular cloud from an extragalactic distance, you would say those stars are still associated with a molecular cloud, even though within the galaxy there's a big hole in it. So it's important to understand when you're putting together galactic and extragalactic that when we say correlations between molecular clouds and star formation, you're talking about an 100 parsec resolution map. You are, in fact, getting decorrelation on small scales if you go to much smaller scales.
Philip, yes.
Hi, Mark. I have a question about the star formation efficiency per free-fall time. You emphasize that it's remarkably uniform among GMCs, but for an extragalactic GMC, which is basically unresolved, how do you determine, for instance, the free-fall time? There is a distribution of free-fall times.
Right, so that's a good question. Let me go back to that. So, all right, you have a couple of ways depending on what your data look like. All right, so if you're talking about these extragalactic observations, the way the freefall time is estimated is these are sort of 100 parsec scale pixels, so it is simply estimated from hydrostatic balance, that for this 100 parsec scale patch of the galaxy, the midplane density has to be determined from the velocity dispersion and the strength of gravity from hydrostatic balance. So that's one mechanism you can use if you have 100 parsec resolution. If you have better than that resolution, which is true for some extragalactic observations, particularly, for example, in the Magellanic Clouds, you can use the same techniques that are used in the Milky Way, which is you can trace out contours of, say, dust or molecular gas, and then you can say, well, let's guess that the third dimension is comparable in size to the two we can see, and that gives you an estimate of the volumetric density. And in fact, you can even do better than that. You can do statistical corrections. That's what's done in this Hu paper. This is looking at galactic clouds, but there it's looking at the contours, but then using a statistical technique to try and get a better estimate of what the 3D volume density actually is than your sort of naive just extrapolate to the third dimension. So that's how the freefall times are estimated. I should also say there's a completely independent technique which relies on the critical density of HCN, which has its own uncertainties, but those uncertainties are sort of orthogonal to these uncertainties and gives you the same answer.
Okay, question from the back.
Hi, Mark. A question about the feedback. So you mentioned that stellar feedback is dominant in ending the lives of the molecular clouds, and in particular in massive stars. I think we have seen some SOFIA maps of C+, for example, where that show examples of sometimes low mass stars also play a role. Can you quickly comment on what makes you say that generally it's really the massive stars that do the job?
Right, so, okay, what I wanted to emphasize there is the G in GMC. That is simply that if we're talking about the sorts of things you can see in an extragalactic survey, so that is things that are sort of 10 to the 4.5 solar masses and up, there simply isn't enough power to disperse a cloud that big using just low mass star feedback. Now, if you're referring specifically to the SOFIA result, to the C+ results in Orion, that is massive star, right? That's massive stellar winds. Is that what you're referring to?
Yeah, but I think there are also examples of where low mass stars seem important. But these may be special cases.
I think low mass stars can certainly be important in a low mass wimpy molecular cloud. If you're talking about, something that's like the size of Taurus and the density of Taurus, I totally believe low mass stars could be important for them. In an extragalactic survey, Taurus borders on undetectable. So when we talk about giant molecular clouds, we're talking about really things that are substantially bigger than that. And there simply is not enough power in the protostellar outflows to disperse something that big.
Cool, thanks.
Yes.
Hi, Mark. Thank you for the talk. You mentioned about that when the high mass stars form, the dispersal happens quite quickly after that. But when you look at galaxies, you have these galactic spiral arms, and that's where all of the high mass stars are and the GMCs. How do you reconcile this?
So I'm not quite sure what there is to reconcile. You do certainly have more GMCs in the spiral arms, but that's not the only place there are. And you have flocculent spiral galaxies where the GMCs are sort of everywhere. So I don't think it's a true statement that there are no molecular clouds outside of spiral arms. There are, in fact, molecular clouds outside of spiral arms. There are certainly many more in spiral arms, but it's not like that's the only place where they live.
But shouldn't the high number of high mass stars in the spiral arms kill all the GMCs?
And they do kill significant numbers of them. So you do destroy a lot of them probably in spiral arms. But it is not the case when you do the statistics of the correlation that molecular clouds all die immediately, in 5 million years. They die pretty quickly once you have optically revealed massive tracers of massive star formation, but there seems to be a long period before that when they live.
Thank you.
Yes.
Hi, Mark. Thanks for the excellent talk. I was wondering how this discussion of the star formation efficiency per freefall time sort of interacts with the ambiguous boundaries of molecular clouds. So does the way that you define these clouds interact with this sort of universal 1% star formation efficiency?
Yes, that's a really good question. So if you want to get this right, you do need to worry about how you define your clouds, and you need to be very careful to define your clouds and your star formation tracers consistently. So what's done, for example, in this Hu et al. Paper is to draw contours at different surface density levels. That's what's on the x-axis here. And then count how much mass is there within that contour, what is the mean free fall time of that mass, and then what is the star formation rate counting only stuff within that contour. And so you need to be extremely careful to be consistent in how you measure each of these three things and measure them within the same contour. And if you do that, you get that it's about 1% with no strong dependence on contour. But it is critical that you do all of that self-consistently. If you only used contours for one of these and not the other two, if you weren't consistent, this would go all over the place. You have to be consistent in measuring the mass, the free fall time, and the star formation rate in the same way within the same volume.
No one is standing in front of a microphone? Okay. Okay, could you show the front page? First page. Yeah. So this is very nice, fancy picture. But I don't think you connect your talk to this chain or bubble picture.
Yeah, so I didn't really, because we made a decision to try and have the talk reflect what was in the chapter, and the chapter was written, before this picture existed. Mm-hmm. If you'd like me to extemporaneously try and do it now, I can comment that, so I see, for example, these huge holes blown clearly by supernova feedback.
Yes.
All right, and those are dominant on galactic scales, but the molecular clouds are sort of living at the edges, and it's not totally clear, for example, how much those molecular clouds are influenced by these holes. Are the holes actually dynamically influencing them, or just saying where the gas can be, and then the molecular clouds form where the gas is?
Okay. I have to disagree, but okay, we have time.
Fair enough.
Okay, so now it's up. So let's thank our speaker again.